really look forward to your talk.
Thank you very much for the introduction. And I should say, we had a little poll just before we started, right? And the majority of you indicated that you had never done a Bayesian analysis. And the same actually was true for me. Even though I was promoting Bayesian analyses, my practical experience in actually carrying out a Bayesian analysis, it wasn't very strong at the time. And that's a general problem for the field. The philosophical appeal is really high, but then what do you do when you have a concrete research problem and you want to conduct a specific analysis? Right? How do you do a Bayesian ANOVA? How do you do a Bayesian t-test? And in order to address that obstacle, overcome that obstacle, and make it as easy as possible to do Bayesian inference and also to teach Bayesian inference, we've developed JASP. But I'm getting ahead of myself. Let me just give you a proper introduction first. So I'll share my screen. I hope everybody can see this.
Looks good.
Great, because I cannot see the chat, so I'm flying blind here. I do like questions in between, so please, if there are interesting questions, maybe the moderators or the panelists can just interrupt me and ask those questions as they come up. So tips and tricks for teaching Bayesian statistics. So first, I'll answer the question what Bayesian statistics is. Then I'll have one slide about why you should not teach Bayesian statistics, and then a few slides on why you should. And I'll discuss opportunities and obstacles. And throughout, I hope to illustrate my arguments with a demo in the JASP program. And I'll even show you some of the material that you cannot find in JASP just yet, but it will be in our upcoming release. So what is Bayesian statistics? So my favorite definition is from Pierre-Simon Laplace, who said that it was common sense expressed in numbers. And I thought, just for the heck of it, I'm going to do something that I almost never do. I'm going to quote a long fragment here from Laplace. This is how he ends his book on the use of probability theory in all kinds of real life situations. So he ends as follows. So there's two slides on this. So I actually cannot see the first line because it's blocked by my, let me see whether I can, yes, I can move that. Okay, it is seen in this essay that the theory of probabilities is at bottom only common sense reduced to calculus. It makes us appreciate with exactitude that which exact minds feel by a sort of instinct, without being oft times to give a reason for it. It leaves no arbitrariness in the choice of opinions and sides to be taken, and by its use can always be determined the most advantageous choice. Thereby it supplements most happily the ignorance and the weakness of the human mind. Okay, and now comes his final sentence. It's only one sentence. Here it is. If we consider the analytical methods to which this theory has given birth, the truth of the principles which serves as a basis, the fine and delicate logic which their employment in the solution of problems requires, the establishments of public utility which rest upon it, the extension which it has received and which it can still receive by its application to the most important questions of natural philosophy and the moral science. If we consider again that even in the things which cannot be submitted to calculus, it gives the surest hints which can guide us in our judgments, and that it teaches us to avoid the illusions which oftentimes confuse us, then we shall see that there is no science more worthy of our meditations, and that no more useful one could be incorporated in the system of public instruction. So I think this is beautiful, and it shows you how enthusiastic Laplace was about this topic. And I think when it comes to teaching statistics, I think we need to adopt the attitude of Laplace, right? How privileged are our students that they can be instructed in this topic. But of course, Laplace wasn't talking about frequentist statistics. It didn't exist back then. He was talking about Bayesian statistics, the field that he basically founded. So another definition of Bayesian statistics, a bit more prosaic, is that Bayesian statistics is when you use predictive performance to update your knowledge about the world. And this idea that you use predictive performance to update knowledge is central to my children's book, Bayesian Thinking for Toddlers, which started as a dare. This is the end result. It's freely available on that link below, but if you just Google Bayesian Thinking for Toddlers, I'm sure you'll find it. And I'm not going to read the children's book to you, but the idea is that accounts that predict the data well increase in credibility, and accounts that predict the data poorly suffer a decline. And that's the central idea. And you can also visualize it as follows. Through a learning cycle. So we start at the top with our prior knowledge. And from our prior knowledge follows a prediction. This is really important because without prior knowledge, you can't make a prediction. The prediction follows from the prior. So we make a prediction. That is a deductive process. And then we are confronted with data. And the comparison between the prediction and the data gives rise to a prediction error that then, in an inductive fashion, causes a knowledge update, which yields to posterior knowledge. But it's only posterior to the data that you just saw. That posterior knowledge becomes the prior knowledge for the next batch of data. And this way, the cycle of learning can continue indefinitely. So this is Bayes' rule written in a slightly different way than you may be used to. So there's 3 ingredients to Bayes' rule. We start with our prior beliefs about theta with Greek letters, right? We denote whatever it is that we're unsure about, that we want to learn about, an account of the world, a claim, a proposition, a parameter value, a hypothesis, a model. So it's something we want to learn about. So we start with some prior beliefs about it, and we end up with posterior beliefs, the plausibility of the different values of the parameter after we have observed data. And Bayes' rule tells us how we go from our prior conviction to our posterior conviction. And how do we do this? Well, we look at how well this particular account that we're interested in predicted the data. More concretely, we look at the prediction for the observed data, and then we say, if we condition on this specific account of the world that we're interested in, theta, if we condition on it, what happens to our predictions? Do they become better or do they become worse? If they become better, then this predictive updating factor is higher than 1, and our belief increases from prior to posterior. But if conditioning on that account of the world makes the predictions worse, then the predictive updating factor is lower than 1, and our posterior credibility is lower than our prior credibility. Now we can move that, this term, our prior beliefs, we can move that over to the other side, and we get this. So this, this rule says that the change in our conviction about a particular state of the world due to having seen the data, so the support that a particular proposition gets from the data, equals the predictive success from that particular account of the world. Right? So, in other words, if we look at the right term here, if this account of the world makes your data less surprising, more predictable, then that account of the world has become more plausible, has gotten more support from the data. So in words, you can say that surprise lost is credibility gained. Right? So surprise is sometimes a good thing, but in statistics, it's a bad thing. You don't want to be surprised. So The more surprise you lose, the better it is. Surprise lost is credibility gained. And I'm just showing this to you because this is just one way in which you can show that common sense follows from Bayes' rule. There's other lessons that are hiding inside Bayes' rule that are also very important, such as extraordinary claims require extraordinary evidence. But I won't go there for this presentation. I just wanted to keep this section really brief. If you want to learn more about it, I recommend this paper by Jeff Rauder and Richard Morey, Teaching Bayes' Theorem, Strength of Evidence as Predictive Accuracy. So, I have one slide on why you should not teach Bayesian statistics. So, the first one is a comment that I have gotten from my colleagues. Because, of course, it is my goal in life to teach as many students as possible as much of Bayesian statistics as possible. But sometimes I find that my colleagues aren't as collaborative as they should be. And one of their arguments is that the field, at least the field in psychology, is not Bayesian. So why are we going to teach students something that they don't need? Well, you may think this is a good point, but if we all accept this as valid, then nothing will ever change, obviously, because we just practice what we teach, and we teach what we practice, and that obstructs all change. But it is true that you will have to adjust or replace your current teaching materials because they probably aren't Bayesian. And you may even have to school yourself in a statistical method with which you are not yet familiar. But there are also good reasons to consider teaching Bayesian statistics. Your students will love you, statistics will suddenly make sense, and your life will be more fun. And I think these are three strong reasons to consider a shift to Bayesian statistics, or at least include it in the statistics curriculum. I had to fight tooth and nail at my institution first to get some Bayesian materials into the second year, and then it turned out that students absolutely loved it. And at some point it was put to a vote, do you want to see Bayesian statistics in the first year? And I think there was an overwhelming majority of students who said yes. So now we actually have several classes of Bayesian statistics for our first year undergraduates at the University of Amsterdam.
Eric, I'm sorry to interrupt. There is a question that came up about Bayes factor. Would you like me to read it out? From Rosemarie, I've been told that the Bayes factor is similar to the p-value because of the priors that we in psychology more or less guess. Also, the Bayes factor has thresholds where up to a certain number, whatever you're testing is not significant, kind of like the 0.05. What do you think about this similarity between the Bayes factor and the p-value?
Right. Well, I think the ultimate goal is the same. The idea is basically that unless you provide positive evidence to the contrary, the skeptic's null hypothesis holds the field. So if you're a researcher and you want to say, you want to make any claim, then you have to offer positive evidence for that claim, right? And that usually means that you have to show that the skeptic hypothesis does relatively poorly. With a Bayes factor, the emphasis is on relatively poorly because you compare the hypothesis of the skeptic to the hypothesis of the proponent. And this is different from the p-value that only looks at the hypothesis from the skeptic, right? So there are real philosophical differences between the two, but there's also philosophical similarity in the sense that they both would adhere to Occam's razor. So if you don't have positive evidence to the contrary, you stick to the skeptic's hypothesis. With respect to the thresholds, basically with Bayes factors, I would say you could do whatever you want. It's a continuous measure of strength of evidence. It is true that to help the interpretation that discrete levels have been proposed, but in the end, it is what it is. So a Bayes factor of 3.1 or a Bayes factor of 2.9, in my mind, they're virtually identical. So I would definitely, that's one of the pitfalls though, which you have with p-values as well. You want to avoid the cliff effect, right? Rosenthal called it the cliff effect, I believe. But we are really getting ahead of ourselves because we're nowhere near Bayes factors yet.
Okay, great. And another attendee asked if they're interested in understanding Bayesian statistics before teaching it, is it recommended, do you have a recommended starting point or a crash course to get started?
Yeah, I do, and I refer to several introductory materials at the end of this presentation, but I can already tell you that the one that I like best, I can't show, well, I can show it to you, but you probably won't be able to read it because of my camera. So it's this one, and it's Bayesian Statistics the Fun Way by Will Kurt. I reviewed it recently for my blog, Bayesian Spectacles, and I really like it. But you know, what you need to prepare completely depends on the level of your students that you're teaching, obviously. So, but for first year students, for undergraduates, I think the Kurt book is a really good start. And I would even recommend it as a textbook when you want to focus on the concepts. If you, if you want to do a more complicated material, then obviously you need to prepare better.
Okay, great. And I think one more before we can proceed. Surely one reason for many people's distrust in formative priors, what about using the likelihood ratio, which unlike p-values measures evidence and doesn't need an explicit prior?
Well, that's right, but that's right. So you could look at the likelihood ratio, and in fact, the Bayes factor is a likelihood ratio. It's just an average likelihood ratio. Because the problem with the likelihood ratio is, okay, we have the prediction for the observed data under the null hypothesis, and now we want to contrast that with the prediction for the data under the alternative hypothesis. And because we're doing a likelihood ratio, we need to choose one particular point, one particular effect size, say, with which we are going to do this, right? Which one do you pick? The maximum likelihood estimate, you could pick that one, but it will obviously be biased in favor of the alternative hypothesis. So then you have to apply some correction. So which one do you choose? And so the nice thing about the Bayesian formalism is that it kind of solves that issue. It kind of, by averaging across the prior distribution, this is like a correction for multiplicity. So I would agree that the evidence is in the likelihood ratio. But yeah, I don't think we have a crystal ball where we can just pick one value and say, this is the one we're interested in. You could plot something across the entire range, but then the question is, what conclusion do you now attach to this, right? So, yeah. But I mean, these are all fascinating issues, right? And in my, and I'll get to that at a later stage, students are surprisingly interested in these things. I think what students, and I speak from my own experience as well, what students aren't interested in, and what I certainly wasn't interested in as a student, is kind of the Searle's Chinese room way of teaching statistics, right? Where you get some inputs, you do something mechanically, and there's some outputs without you know, knowing why you're doing things or how you should interpret them or what the alternatives are. And it's often very refreshing for students to see that there's a debate. And I firmly believe that if we want to really teach our students classical statistics, we have to teach them Bayesian statistics as well, because it's only through the contrast between the two approaches that you really know what a p-value is. Because if you're not taught what the Bayesian perspective is, you will simply misinterpret all the classical statements as Bayesian statements, in my opinion. Okay, so that relates to the following slides. There are a number of pragmatic Bayesian advantages. Maybe the most important one is that you're able to attach probabilities to parameters and hypotheses. You can quantify evidence for any hypothesis you care to specify. You can learn, you can update your beliefs, and you can keep going indefinitely. So you can monitor the evidential flow as the data come in. I think these are all things that I believe humans do naturally in their personal life. It's only when they become frequentist statisticians that they stop doing this, and that they even condemn doing so. Okay, so on to our opportunities. So first we need to answer the question, how do we best teach Bayesian statistics? And the answer depends on who you ask. If you ask a mathematician, they would say, well, you need to teach students mathematical statistics so they can mathematically derive posterior distributions. If you ask a programmer, they would say, well, you need to teach your students R, Python, Stan, or JAX, or methods to design their own Markov chain Monte Carlo techniques. And even though that this may make perfect sense for students in mathematics or students in AI, for our field, for psychology, this does not work. In my opinion. In my opinion, even the programming approach, it puts a second load of difficulty onto a topic that most students already feel is pretty intimidating. So the solution, obviously, is JASP. So you can find more information at the website jaspstats.org, which is a hub for all things related to JASP. And that we enjoy that, of course. So as is clear from the logo here, JASP offers both classical frequentist statistics and Bayesian statistics. I'm going to emphasize the Bayesian routines in this talk, but we offer the classical ones as well. And honestly, I think that most universities that use JASP for teaching right now use it because of the classical analyses. And here you see a snapshot of the team of people that is working on JASP. It's outdated, new people constantly enter, other people leave. But the general idea is that there's lots of people working on JASP. And that is also needed because it takes a tremendous amount of effort and time. Only the upkeep of the software to make it still run when new operating systems are updated, only that is already a substantial effort. So you can help JASP. And the easiest way is to let me know if you have suggestions for improvement or if you want to contribute in some way. And we have a GitHub page, and you can post feature requests and bug reports there. You can also follow JASP on Twitter or Facebook, and read our weekly blog post. Well, that was a little optimistic actually when I wrote this. It's not weekly because we're just too busy programming. But you can keep up to date with our blog to know about the latest developments. This is a world map that shows the universities. I think we're up to 100 and actually we're up to 194 now from 55 different countries that have emailed us to tell us that they're using JASP in their curriculum. So the real number must be much higher, but I can't tell you anything about that. So like I said, we offer both classical frequentist statistics and Bayesian statistics, and I didn't want to do that at first. I just wanted to present Bayesian statistics, but I was persuaded by the Trojan horse analogy, where we offer both, so that people who teach frequentist statistics or students who use it for frequentist statistics will see a button where they can execute a Bayesian analysis, and they wonder what will happen if I press that button, and then hopefully we can entice them to take a closer look. And in general, I have to say, when I'm more objective, I would say that it is prudent to look at your data from different perspectives. So that includes different statistical paradigms. So yeah, that's the idea. So now I will show you JASP in action, and I'm going to do this with a data set that involves Adam Sandler. So, and it's discussed in this paper, Bayesian Benefits for the Pragmatic Researcher. And there's a history to this data set. My goal was to find a data set where there is no experimenter. Data come in over time. So let's say nature gives us these data, and we have no control over it. So that makes it difficult to use classical hypothesis testing, because what is the sampling plan here? Right? It's undefined in a way, or if it's there, it's beyond your knowledge. But for the Bayesian knowledge updating approach, this is not really an issue to worry about. So what I've done, and this is based on an elaborate cover story involving South Park, but I won't go into that. I'll just tell you that there is a hypothesis that says movies with Adam Sandler are profitable regardless of their quality. So the correlation between movie quality and box office success is 0 for Adam Sandler movies, which is strange, a strange hypothesis, because you would say more people go to see good movies. But anyway, I looked into this hypothesis, and let me just start JASP and tell you what I did.
Eric, there's a JASP question, if I can cut in. Is JASP a GUI for R, or is it its own program? For example, Jamovi is a GUI for R and can provide the exact R code if you wish. Is this possible with JASP? Yeah, absolutely. JASP is a GUI for R, and Jamovi is a clone of JASP. And so they work from the very same principles. And so we even have, so if you go here to the plus sign, we have we have an R console over here, and we are currently working on making the R syntax available, and that will not be available in the next version of JASP, but the version after that. Right. So I was going to show you the Adam Sandler data set. So I should say, I don't want to say anything bad about Jamovi, right? So the programmers from Jamovi are actually the programmers that I hired to start the JASP program. So they're excellent programmers, and they did a fantastic job, and I wish them all the best. So we go to the data library, and we have about 50 data sets here, and there's a book that describes the data sets, and this is meant to facilitate teaching. So we go to regression, and here the first data set is the Adam Sandler data set. I will just click on the data file. If I click on this item, open JASP file, I get all the analyses, annotations, interpretation, but I don't want to spoil the fun. So I'm just going to click on the CSV file, and you see a spreadsheet here with the year the movie came out, the freshness ratings on the movie website Rotten Tomatoes, where 0 means nobody liked it, and a 1 means everybody liked it. Box office success in millions of dollars, and the movie title. So for instance, in 2005, the movie Deuce Bigalow, European Gigolo came out, and it had 9% fresh, and it scored 22 million at the box office. Right. So we can, before we do any analyses, it's a good idea to look at descriptives. So you see we can now select the relevant variables, let's say freshness and box office success, and we drag them over, and immediately there's an output table that pops up, where you see that a summary of the data, the mean, standard deviation, minimum, and maximum. And in JASP, it's easy to adjust this table. For instance, if we open the tab statistics, we could say, well, we don't want the mean. So we untick this box, the mean disappears from the table. We want the median. We tick the median, and the median is now inserted in the table. Right, so we can construct a custom table however we want. We can also annotate all of these elements. We could also copy this APA style table to our Word document. We can copy the LaTeX code, but we can also add notes. I usually just say, this is a wonderful table, but obviously you can also use this functionality to annotate your analyses, to describe what your variables mean, to ask questions to students, which students can then answer, those kinds of things. Here, before we do a particular analysis, because we're interested in the possible relation or absence of a relation between freshness and box office success, right? So we can look at some plots. So let's just look at a scatter plot.
right? So we see the freshness versus box office success, and this may be hard to interpret. We can use a linear regression line. This is more usual to do this, and you can see that there's not really anything going on here. If you squint, you may even detect a slightly negative relationship in this sample. And as before, you can adjust this graph in several ways. So in the upcoming release of JASP, we'll have several more graphs like rain cloud plots, and I'm very enthusiastic about another new feature of the program, and that is a graph editor. So currently, if you select you can do save image as, and then you can select all kinds of formats. But in the upcoming release, we will also have a button that says edit image. And when you press that, you get a little editor and you can change the axes and stuff. So it's really cool. Okay, so there's not much going on here. But the question now is, do we have evidence in favor of the null hypothesis? And if so, how much? So now we're going to use Bayesian inference to differentiate between evidence for absence, right? Evidence that there's nothing there, or absence of evidence. Are the data relatively uninformative? So you see that on the ribbon, there are all these analyses: t-test, ANOVA, mixed models, regression, frequencies. There's actually many more, and you can add and remove some of them by ticking these boxes. So for instance, we don't need SEM, and I don't need the R console, and well, let's just remove all of them, right? So this is the basic set, and for most of these tests, we have tried to have a classical frequentist version and then a Bayesian echo. So we offer different t-tests in classical and Bayesian form. Same for ANOVA, same for mixed models, and for regression. And for regression, we're going to choose Bayesian correlation. So freshness and box office success go in here. So I'm quickly going to go to plot individual pairs here, because we're not interested in a huge matrix, correlation matrix. We really want to focus on two variables. So JASP automatically gives you the scatter plot by default, because this box is ticked by default. And this is to protect you from drawing a conclusion that is ridiculous, because the data maybe are not suitable for an analysis at all, right? There's this famous a picture of a dinosaur, the Enscomosaurus, and obviously if you analyze that and you compute a correlation, it's meaningless. But if I untick it, that box disappears, and I can tick prior and posterior, and so this is not a talk about about teaching you Bayesian statistics, but it does show you that it's very easy with one click of a button to obtain a somewhat intriguing a picture of what inference we could possibly draw. And with one click, we can even obtain a sequential analysis. So the sequential analysis basically looks at the evidence that we have. Let me just increase the area for plotting. So this monitors this Bayes factor that we have already talked about, the extent to which the null hypothesis outpredicts the alternative hypothesis. And you see that as Adam Sandler makes more movies, the evidence in favor of the null hypothesis gradually increases. And the interesting thing here is that if we were to go to the Rotten Tomatoes website and look at the movies that he has made since 2015, because I think this is where I stopped after 31 movies. If we were to update our data file, we could just rerun the analyses and new dots would be added to the ones we already have. And we could continue indefinitely until Adam Sandler decides that it's time to stop making movies. So this is a very quick demonstration of JASP, how you can use it to analyze data, and of course also data that are used for an educational purpose. But we can do a little more with JASP, but I'm going to turn to that next. So, because we're on to the tips and tricks section of this talk. So the standard example of Bayes' theorem is binary classification. So, and this is often used, and in particular the importance of taking into account the prevalence of a disease. It's almost always used to show how Bayesian statistics gets the conditioning right. And in particular, what you want in the end is to know what is the probability that I have COVID given that I'm coughing. It's not what is the probability that I am coughing given that I have COVID. So, but in order to know what this is, the probability of having COVID given that you're coughing, we need to have the base rate of COVID, right? If you will, the prior probability. So in the upcoming version of JASP, we will have a binary classification tool, and it's part of the Learn Bayes module. So the Learn Bayes module, we're creating it to make it easier to teach Bayesian statistics. And this is work by Amy and Simon Kucharski. So this is the Learn Bayes module, not the way it looks, what it looks now, but this is the way that it will look. And you see, we offer a number of analysis problems. But the first one is binary classification. And that's the one I will look at now. So we can do binary classification in two ways: the non-Bayesian way and the Bayesian way. So I'm going to discuss the non-Bayesian way first. And it's interesting because the non-Bayesian way is actually the way in which people teach Bayes' theorem. So what we do in the non-Bayesian way is we give point estimates for the three important quantities here: the prevalence of a disease, the sensitivity, so the probability that the test is positive for people who have the disease, and that's the sensitivity, and the specificity is the extent to which you can correctly identify people who do not have the disease. So we have these numbers. Those are just example numbers. And what you immediately get is a table, and you can see in the table the first three numbers are the same that I gave as input, but then automatically you get all these other numbers that people often use. For instance, the positive predictive value and an explanation for what it means. The probability of you having the disease given that the test came out positive. This is the one that people care about usually. You can also get a huge number of figures. It's actually quite elaborate. I only have time to show you a few. So this is a key one, obviously. So the pinkish color, that's the base rate, that's the prevalence. But if you have a negative test, you see that it doesn't really affect the probability of you having the disease very much. Whereas if you have a positive test, it does greatly increase the probability that you have this particular disease, but only to a probability of about 60%. And there's other plots that this module generates, and I'm just giving you an example here. I won't go into detail because I don't have time to discuss this. But I will say that I think that Simon and Amy did a spectacular job in implementing this. And these are then that's basically the visual summary of the table. These are the estimates for a few of those measures that we are interested in. So this is great, but it's not really Bayesian. And why isn't it Bayesian? Because the key numbers were treated as absolute truth. But in reality, we have uncertainty about these things. And if we take that uncertainty into account, it propagates to the measures of interest. So this is when you tick the button uncertain estimates. And now you can actually assign particular prior distributions to these three key measures. And in this case, I used beta distributions, and I tinkered with the parameters in order to have the means of these distributions very similar to the example that I showed you previously. So when I do this, and I'm just presenting the top of the figure, you see that for prevalence, sensitivity, and specificity, we almost get exactly the same number. All right, but this is the mean of that distribution. Here we now also have a 95% credible interval. So you can see that for the prevalence, for instance, the lower bound of that credible interval is at 0.025, and the upper bound is at about 9%, or 8.4%. Right? So that is kind of a rough indication of the uncertainty that you have with respect to prevalence. And you could do the same for sensitivity and specificity. And from, okay, I admit these numbers were actually based on papers about COVID, so I think this is not completely unreasonable. So what does that do? Well, the picture I showed you now becomes a little more subtle, because these bars give you the credible interval, and you see in particular after you've had a positive test, there's considerable uncertainty about whether you have the have the disease or not. So you can show it like this, but you can also show the entire distribution. So it turns out that this uncertainty that I specified at the start propagates to the uncertainty about the final conclusion. And it can be visualized like this. Okay. So the second tip that I have is, what I do almost always is dedicate one class to a debate. And the debate, if you have a small group of students, you can do a debate between two different groups, or you can have a debate between two lecturers. And so Danny Bosboom, my respected colleague, and we do such a debate twice a year. And it's a tremendous amount of fun, and students are really into it, because they see that people can actually differ dramatically when it comes to statistical methods, which is, I guess, refreshing to them. And so this is Danny when he argues against me, and this is what everybody sees, but this is what I see. So I'm trying to tell people that, that the Bayesian way is, of course, better. But Danny is actually a very reasonable person, but he takes an extreme position in this debate, and so do I. Okay, so then I would recommend to try to introduce Bayesian statistics as early as possible, because once students have learned frequentist statistics, it's very difficult for them to open their mind to a different approach. They can still do it, but it's just a little bit more work. So you might have to fight your colleagues for this, but I think it's totally worth it. And like I said, students actually want this, and they appreciate a different perspective. Now, these are some general pieces of advice that apply, whenever you teach anything about statistics, and many of you will know much more about this than I do. So I would like to say that in-class quizzes are interesting and important if you do a good job. Not so much to grade students, but just to, I like to ask them questions, trick questions, and I hope they fall for it. And of course, they catch on at some point, and they start to really think about the questions. And I would say one thing that we have all learned from Andy Field is that the more outrageous the data set, the better students will recall it. So I tend to use either highly relevant or a very outrageous data sets. And I also collect data in class. So I actually wanted to collect data here, but in the interest of time, unfortunately, I think we'll have to skip this. But that is also something that really works well. So for instance, one thing I do is I ask students, do you use Mac or Windows? And then the first one says Mac, and then the next one says Windows, and then the next one says Windows. And I keep track of the uncertainty about the true underlying proportion of students who use a Mac, say. And then you see that as data accumulate, the posterior becomes more and more narrow, and sometimes it still shifts a little bit. That gives students a good idea about what Bayesian updating is all about. So yeah, so I'll skip this demo in the interest of time. And I have this random slide here, but it's not entirely random. This is just to show you what kind of data you can easily get to highlight the relevance of Bayesian statistics. So a question such as the one answered in this medical paper is so this is clearly very important. And then you can see how were the statistical analyses done in this paper. What could you do in a Bayesian framework? How does it differ? And students who aren't interested in something like this, I think that's very rare. So students need to feel that what they're doing is actually important, in my opinion. So obstacles. So the first obstacle, we've already mentioned this. There's actually few course books on Bayesian statistics that do not demand a background in mathematical statistics or programming, and cover both parameter estimation as well as hypothesis testing. And that is my personal bias. I actually like hypothesis testing. I think before I'm ready to estimate a parameter, I first want to know whether I'm just reading tea leaves here or whether there's a signal among the noise. That's me, but I actually also think this is the mindset of science as a whole. So I think people who really argue against hypothesis testing and in favor of parameter estimation, I get what they're doing, but I don't think it will ever fly in the academic literature. My opinion. But what Will Kurt does, he actually presents both approaches. And I think that's really nice. And this is a great book, so I would really recommend it. I would actually recommend it even if you're not going to teach Bayesian statistics. It's just fun to read. I most strongly recommend my own books. There's two of them, Bayesian Inference from the Ground Up, Volume 1 Theory and Volume 2 Practice, with my colleague Dora Matske. The only problem about this is that it's still work in progress. So it's not available right now. Volume 1 is almost done in the sense that it's over 300 pages. But it will probably, realistically, I think it will probably take until after the summer before I'll put it online and I'll advertise it and make it freely available online. And I do think in combination with Volume 2, I hope those would be the go-to resources for teaching Bayesian statistics, certainly with JASP, because what I'm doing in these two books, of course, is to integrate the teaching content completely with the software program. Other papers, the one that has gotten a lot of attention is this one by the first author, Johnny van Doorn, the JASP Guidelines for Conducting and Reporting a Bayesian Analysis. And also, if you're not afraid of constructing a reader, instead of using a textbook, there's this special issue in Psychonomic Bulletin and Review 2018 by Joachim van der Kerkhoven, Jeff Rauder, and John Kroschke. And I think that entire special issue is great. So I would really recommend that. And I think at least some of the papers could be used for teaching. Although I would, for undergraduate psychology students, you know, maybe not, but you can certainly take a look at it. If you want to school yourself, I think there's no better start than this special issue. And then I discovered that there were no more obstacles. Maybe you can think of obstacles, but I was out of inspiration here, and it's much nicer anyway to talk about opportunities than it is to talk about obstacles. So I would like to leave it here and open it up for questions. Thank you very much.
Okay, thank you so much. So there are several questions in the Q&A.